The equilibrium constant K can be expressed in terms of partial pressures if reactants and products are gases. So for the equilibrium process, N2O4 forms 2NO2. We can simply write Kp is equal to the pressure of NO2 squared divided by the pressure of N2O4. So it's still products divided by reactants. I'm not going to go through the derivation to get from Kp to Kc, but here is the equation that will allow us to go from Kp, which is in terms of pressures, to Kc, which is in terms of concentration. Delta N is moles of product gases minus moles of reactant gases. So let's look at this problem here. We have a gas state reaction, N2O4 forms 2NO2. We want to solve for Kp and for Kc. Since we're given the pressures at equilibrium, we're going to do Kp first, and Kp would be equal to the pressure of NO2 squared divided by the pressure of N2O4. So we're going to plug in our numbers, and the pressure has to be in atmospheres when we use Kp, and they are, so 0.238 squared, then divided by 0.5. And just like Kc, Kp is a unitless quantity, so Kp comes out to 0.113. If I want to find Kc, I would take Kp divided by RT raised to the delta N. Kp I just found. R is 0.0821, the gas constant R. T is temperature in Kelvin. We're at 25 degrees Celsius, so 298 Kelvin. Delta N is the moles of product minus moles of reactant in terms of gases, so that would be 2 minus 1. And then we can solve for Kc, which comes out to 0.00462. So there's the relationship between Kp and Kc. We're going to define the reaction quotient, which is Q for the general reaction, as Q equals the products raised to their powers divided by the reactants raised to their powers. K has the same form as Q. The only difference is Q is not necessarily at equilibrium. These can be initial concentrations. So we're going to solve for Q, and that will tell us which way the reaction is going to proceed until it reaches equilibrium. So if Q is less than K, the forward reaction will occur at a faster rate until equilibrium is established. If Q equals K, which is very rare, the system's already at equilibrium, and if Q is greater than K, the reverse reaction proceeds at a faster rate. So it simply tells us which way the reaction is going to go in order to reach equilibrium. So if we're solving for the reaction quotient Q, we go back to my balanced equation, and we're in terms of concentration, so we could do SO2 squared times O2 divided by SO3 squared. So there's my setup for Q based on this particular equation. So we have 0.15 squared times 0.025 divided by 0.6 squared. And so Q, unitless quantity, 1.6, 10 to the negative 3. Which way will the reaction proceed to reach equilibrium? Well, you compare Q to K, and in this case Q is less than K. K was given in the problem as 4.8 times 10 to the negative 3. So since Q is less than K, the reaction will proceed to the right toward the products in order to reach equilibrium. Le Chatelier's principle: when a chemical equilibrium is upset by a change in any factor affecting the equilibrium, the position of the equilibrium will shift in a manner that tends to counteract the change. There are three factors that can affect equilibrium. Concentration is the first one. If this system is at equilibrium, N2 plus 2O2 forms 2NO2, and I add some N2, I disrupt the equilibrium. If I add N2, I'm adding a reactant. The reaction is going to shift toward the right, according to Le Chatelier's principle, to counteract that change. So here's the rules for concentration. If you add something, it shifts in the opposite direction. And if I remove something, it shifts in the same direction. So those are the rules for concentration. So second one here, if I add NO2, again, the system's at equilibrium. Now I'm going to add some NO2. Well, I'm adding a product, so it's going to shift opposite toward reactants. I would produce more reactants until I reestablish equilibrium. And then the third trial here, if I remove O2, assuming we've reached equilibrium again, but I remove O2, if I remove something, it shifts in the same direction. O2 is a reactant, so it shifts toward reactants. Pressure can also affect equilibrium. An increase in pressure will favor the smaller number of gases. So in this first reaction here, we're at equilibrium, but I increase the pressure. Well, if you look at the moles of gases, I got 4 moles on the left side total, 3H2, 1N2, and I got 2 moles on the right side. So if I increase pressure, it's going to go toward products. That means I'm going to produce more products. If I decrease the pressure, it's going to shift opposite toward the 4 moles, the larger number of moles, and that means I'm going to produce more reactants in order to reestablish equilibrium. In the second example, H2 plus Cl2 forms 2HCl. There's 2 moles of gas on the left side, 2 moles of gas on the right side. So if this is the case, if you increase pressure, pressure has no effect on equilibrium whatsoever, if the moles of gases are the same on both sides of the equation. And then temperature can affect equilibrium. In this reaction here, N2 plus 3H2, it is an exothermic reaction. Delta H is negative, so that means heat is a product, so we can put plus heat on the right side. Well, if I increase temperature, I increase heat. That system's at equilibrium, I increase the amount of heat. It's just like with concentration. If you add something, it shifts opposite. So if I add heat, it's going to shift toward reactants. It's going to produce more reactants. If I decrease heat, which is a product, it's going to shift in the same direction toward products. In this example, heat is a reactant. It's an endothermic reaction, so I could put heat over here on the reactant side. So because it's positive. So if I increase temperature, I increase heat. Well, if I increase heat, it shifts opposite. Well, opposite of a reactant would be toward products. And if I decrease temperature, it's going to shift toward reactants. So concentration, pressure, and temperature can affect the equilibrium position, and it will shift accordingly to reestablish equilibrium. The effect of a catalyst will not shift the equilibrium position. It has the same effect on both the forward rate and the reverse rate. It speeds it up. It will cause the system to reach equilibrium more quickly, but it doesn't affect the equilibrium position. It's not going to shift left or shift right with a catalyst. When you have a heterogeneous equilibrium established, that means the reactants and products are in different phases. So for example, when calcium carbonate is heated in a closed vessel, the following equilibrium is attained. Well, the concentration of pure solids and liquids do not change as the reaction proceeds. So we actually leave out solids and liquids in the K expression. So we could write Kc for this reaction as simply the concentration of CO2. Or we could write Kp as the pressure of CO2. But we exclude solids and liquids from the K expression. You only include gases and aqueous.